Okay, guys, we're finishing up our Chapter 2 practice test, and we have arrived at question 12. So it's quite a lengthy one. So we're going to, expect a pretty long video, and let's get started over here, okay? So the average rainfall for downtown Los Angeles, DTLA, if you're not from Los Angeles, over the last 141 years is 14.6 inches with a standard deviation of 6.9. LAX, which is the international airport in Los Angeles, has an average rainfall in the last 73 years of 11.7 inches and a standard deviation of 6.4. So we're going to assume that the distributions of rainfalls for both locations are normally distributed. Part A, what proportion of years did downtown Los Angeles receive more than 10 inches? Also, how about between 10 and 15 inches? Part B, if 12 inches is 1 foot, let's find the mean and standard deviation in feet. C, let's use that mean and standard deviation to approximate how many years downtown Los Angeles received less than 0.4 inches of rain. Letter D, what is the 40th percentile for the amount of rainfall at LAX? Okay, so we're switching to LAX now. And letter E, assuming the rainfall in LAX is normal, follows a normal distribution. They already said that, so yeah. Let's estimate Q1, the median, and Q3 rainfall amounts. And F, in the unusually wet 1982 to 1983 season, downtown Los Angeles received 31.5 inches of rain, while LAX received 25.6 inches. Find the percentile rank for the 82-83 rainy season for both locations, and which location had a more unusual rainfall. So let's start off by what was that one from the other day? Let's start eating our first bite of the elephant. Let's start with letter A. Just like every other problem that you've seen me do with a normal distribution, I am going to take this and put everything on a normal curve, standard z-scores on top, normalize or the contextual data on the bottom, and we're going to locate the relevant contextual data. So where is 10 inches of rain? 10 inches of rain, well, that's going to be somewhere between 7.7 and 14.6. So we can, we don't have to put it exactly where 10 is, but let's say 10 is right about here. And we want to say more than 10 inches of rain. So more than 10 inches of rain includes all of this greater. So there are a few things we don't know, and most notably we don't know the z-score, and we don't know the area. After we write this, we're going to write our z-score formula. So the z-score is equal to our 10 minus the mean of 14.6 divided by a standard deviation of 6.9, and that's going to get us the yellow number on top of the curve. Once we have that yellow number, we're going to write our probability. So the proportion of z greater than our yellow number, that's going to be equal to, well, what's going to amount to our answers. And let's just make that green. We're also going to write the same thing in context, the proportion of rainfall years that is greater than, and in this case, the amount of rainfall, we know it's greater than 10. That's going to be equal to, again, the green. Just notice that actually I've already said that that number is the blue number, is in blue. So I think we're ready to go with our calculations. So let's get to our calculator. So the first thing is to pull up our fraction bar. If you don't know how to do that, it is second y equals and number 1. And we're going to need the mean minus the standard deviation. No, the data minus the mean. So the data was 10 inches. The mean was 14.6. And then our standard deviation was 6.9. So this should give me the z-score of negative 0.667. Let's put that z-score where it belongs in our diagram, negative 0.667. That is in the yellow pieces, negative 0.667. All of that data is the same. Anytime we need a z-score, it's negative 0.667. And now we're going to use our calculator to compute area. We'll do this twice just to make sure we're not crazy. Second, vars, normal CDF, because we're going from a z-score to an area. Whenever the product is area, that's CDF. The lower bound in terms of the z-score was at negative 0.667. The upper bound is the biggest number my calculator has, which is 1 times 10 to the 99th power. We're doing this in terms of z-score, so 0 and 1 for the mean and standard deviation. That gets me an area of 0.7476. And again, we're going to do this a second time just to make sure that we got this, all the normalization correct. So we're going to do our normal CDF. This time we're going to put everything in context. 10 inches. The biggest number my calculator has, because there is no upper limit to the amount of rain you can receive. Well, I guess there is an upper limit, but we're just gonna put it 1 times e to the 99. The average rainfall was 14.6, and the standard deviation for the rainfall was 6.9. And we should get the same number, yeah, 7475. So pretty close. Close enough for us to work with. 7475. This was 0.7476. This was 0.7475. They came from different calculations. So we can answer this now with a summary statement. So in 74.7% of the years, and we really should say about, in about 74.7% of the years, downtown Los Angeles received more than 10 inches of rain. So double check, make sure we got our 4 things. We've got our diagram, we've got a z-score, we've got probability calculations, we've got a summary. Those are the 4 things we're looking for. So we're good to go. There's a second part to this, and that's between 10 and 15 inches. So we're going to start by making a new diagram. Oh, I almost forgot. This is 0.7475 or 76. I'll put a 0.76 there. And like I was saying, for the second part here, we're going to make another diagram, and let's see what that looks like. This time around, we want to know between 10 and 15 inches worth of rainfall. And we already know that the z-score for 10 inches is negative 667. So now we'll do a similar transformation, or solving for the second z-score, which we'll call z2. And that's going to be 15 inches of rain minus a mean of 14.6 divided by a standard deviation of 6.9. That got me 0.58. So next we're going to write our probability statements. So the proportion in under the z curve between negative 0.667 and 0.058, that's going to be equal to the area that we have in green. And that's going to be equivalent to the proportion or the percentage of rainfall between 10 and 15. So now we're going to go to our calculator and we're going to calculate that. Let's see our calculator. And second distribution, normal CDF. First, let's do this in terms of z-score. So that's negative 0.667 and 0.058. Mean of 0, standard deviation of 1. We'll push paste. And that gives us 0.2707. Okay, now that I have that first one, when I do rainfall, when I do the numbers in context, I should get something similar. So let's do this same calculation in context. And that would mean we are between 10 inches of rainfall and 15 inches of rainfall. The mean amount of rainfall is 14.6 inches with a standard deviation of 6.9 inches. And we should get something. So, yep, pretty much the same. So 2706 this time. 2706. So, which number do you want to leave? It doesn't much matter. They are close enough where they should be both counted correctly. Remember, we're talking about statistics. We're not talking about calculus where we have crazy rounding rules. So 0.270. Let's write our summary statement. So DTLA received between 10 and 15 inches of rain in about 27.1% of years. Notice that I'm using the word about to signify that I have numbers which are rounded. These are only approximate, but they should be pretty close. So let's take I mean, that's a lot of work for part A. Hopefully the rest of these aren't going to be as labor intensive. Let's take a look at part B. Okay, part B says 12 inches is 1 foot. What are the mean and standard deviations? And to remind you about those conversions, if you are adding and also multiplying each of the pieces of data in your data set, then the new mean is just going to undergo that exact same transformation. A plus B times the old mean. The new standard deviation is just going to be the multiplier. The A, whatever you're adding or subtracting to your data does not affect the standard deviation. The only thing that affects the standard deviation is the multiplier. So here we're saying that if the new data is equal to A plus B times the old data, then the new mean is A plus B times the old mean, and the new standard deviation is just B times the old standard deviation. Well, if we're converting from inches to feet, that means the new data is going to be the old data times 1/12 or divided by 12. So 14 inches should be somewhere around 1.2 feet. So this makes sense that we would be dividing. Always do that quick mental check to see if the numbers should get bigger or should get smaller. So looking at that, let's make this look even more like our formula. The new data is equal to 0 plus 1/12 the old data. This tells me A equals 0 and B is equal to 1/12. So if I want to find the new mean, So the mean in feet that's going to be 0 plus 1/12 the mean in inches. And then the standard deviation in feet, that's just going to be 1/12 the standard deviation in inches. Okay, so let's make all of those calculations with our calculator. And we get ourselves a mean of 1.22 feet and 0.58 feet. Again, do a dummy check. Make sure, does 14 inches sound like 1.2 feet? Yeah, that does make sense. How about does 6.9 inches? Does that sound like it's going to be 0.58 feet? And yes, it does. So here is our answer for part B. Let's take a look at the next question, part C. So using the mean and standard deviation that we just found, approximately how many years did downtown Los Angeles receive less than 0.4 feet of rain? So we still have an approximately normal distribution, so we're going to use those exact same 4 steps that we used before, starting with the normal curve. Same normal curve, but this time we have our standard deviations marked off in feet. And now we have to find 0.4 feet. 0.4 should be less than 0.64. So somewhere around here. I don't know exactly where, but I'm going to pretend that I know that it's right about here. So that's about 0.4 feet. We don't know the z-score for that, so we'll have to figure that out. Let's write out, first of all, our z-score formula. So we got the z-score for a rainfall of 0.4 is equal to 0.4 minus 1.22 divided by 0.58, and calculating that you get a z-score of negative 1.414. Now I neglected to shade, but we want to know the area less than that z-score. So let's figure out that area less than the z-score. So we get them set up with our proportion of the under the z-curve that's less than negative 1.414. That's equivalent to the percentage of years with a rainfall less than 0.4. And that gives us the green area. And when we grab our calculator, let's see what we get. In my calculator, let's clear things off a little bit. I was getting really messy there. So we want to know the proportion under a z-curve less than negative 1.414. Okay, something went wrong here, so let's check it out. Go to, that'll tell me what's wrong here. Negative 1.41. Oh, inverse norm. I did the wrong calculator function. Okay. Distribution norm CDF. The lower is negative infinity. Yeah. The upper is that z-score, which is negative 1.414, 0 and 1, because I'm looking at z-scores. Paste. And that gives me 0.0787. Let's do the same thing in context. And we should get something similar. Rainfall has to be a number greater than 0. And we're going to go to 0.4 inches. The mean was 1.22. And the standard deviation was 0.58. So we should get a number that's similar. Probably going to be a little bit different because our lower bound here is 0. And we're probably cutting off a little bit of the curve. Let's see how close we get. Yeah, actually not very close at all. So 0.061 versus 0.786. Let's see if we found any errors. Maybe there was a problem with what we did. So what I've noticed is probably where our error is coming from is because we were stopping at 0. If we go back to the same calculation here, and instead of saying 0, we said negative, the smallest number in our calculator, which is negative 1 times 10 to the 99th power, and we did everything else the exact same way, you're going to notice we're going to get a number that's much similar, much better equipped, or close to the actual, or at least the value that we got using z-scores. So what's the correct answer? I would probably lean closer to 0.060. No, that looks like it's going to round to 0.61. So let's go ahead and write that down. Again, I would probably favor that 0.61 number simply because the number is in context. If you're worried about whether choosing one over the other is going to ruin your test score, it's not going to ruin your test score. Whoever is going to be reading your test will be reading for both of these numbers. They should be well aware of the fact that there is going to be some clipping of the area due to that 0 floor for the actual rainfall. So let's write our summary statement here. We get that downtown Los Angeles receives less than 0.4%, 0.4 feet of rain in about 6.1% of years. So feels a little bit unsatisfactory, but believe me, the fact that there are 2 answers here is not really a problem for AP Stats. Let's take a look at letter D. So letter D, what is the 40th percentile for the amount of rain in LAX? Well, now we're going to have a whole new normal curve for LAX. So let's draw that real quick. First of all, here's our normal curve. We have a normal distribution for the amount of rainfall in LAX with a mean of 11.7 and 6.1. Let's write down a couple of things here. First of all, the mean, 11.7. And let's start adding 6.1. Now that we've added 6.1, we're going to subtract 6.1, go the other direction. Just like last time, we're running into a little bit of a problem in the negative side here. You'll notice that we've got a z-score of -2 is negative 0.5 inches of rain, which of course is impossible. So there's going to be some problems here when we compute area on the left side. Now we're asking for a 40th percentile, which would mean I've got to pick a place where the area to the left of the curve is about 0.4. And, this is at z-score 0, that's 0.5. So I'm going to just put 1 here between a z-score of 0 and a z-score of -1. And we're going to say this area here is 0.40. And we don't know a whole lot here. In fact, we don't know what the z-score is, and we don't know how much rainfall that is. So we're going to figure those 2 items out, and we're going to do the exact same things. We're going to write down our z-score formula, and we're going to write our probability formulas. We're going to do, of course, 2 probability formulas. And let's see what those look like. So you notice that these have a lot of holes in them, especially in the z-score right over here with the z-score. We've got 2 holes in very critical places. But if we go down to the area and the proportion stuff, well, there's really only 1 hole to fill, and that's why we're going to be using our inverse normal calculator instead of our normal CDF calculator. So So let's go ahead and grab our calculator and let's try and figure things out. Inverse norm is the correct calculator because we're going from the bottom up if you're looking at that visually. The area we know is 0.4. We're finding a z-score, so that's 0 and 1. And that gives us a z-score of negative 0.253. Negative 0.253. So that tells me this number here is negative 0.253. This number here is negative 0.253. And this number here is negative 0.253. Let's do the same thing, but with the contextualized number, and that will give us an amount of rainfall. So the exact same calculation, except for now we know that the mean is 11.7 and the standard deviation is 6.1. That gives us a rainfall of 10.2. So 10.2 inches, 10.2 inches, 10.2 inches. Summary statement time. So a year with 10.2 inches of rain is at, remember, at the 40th percentile. So notice how the work kind of got done backwards. Normally we start from the top and we go down, but this time we started from the bottom and we went up. So that's indicative of we have to use our inverse normal calculator. Let's take a look at letter E. So assuming that LAX is following that normal distribution, let's estimate the Q1 median and Q3 rainfall amounts. So let's start by calling up that normal distribution curve that we just used in part D. These two diagrams are going to help us find our 25th percentile and our 75th percentile, which is our Q1 and our Q3 respectively. Since there's a lot to do in this problem, I'm not going to mess around too much with figuring out the z-score and all of that business. I'm just going to go right to well, I'm going to lie a little bit. I am going to find out both the z-score and the amount of rainfall for both of these. The one I'm not going to do is the median, because in a distribution that's symmetric, the median is about the same thing as the mean. So we know the median is about 11.7 without even doing a whole lot of work. Let's start the real calculations with our Q1, which is the 25th percentile. So as you can see, I've set up the proportional statements, the proportion probability statements for both a z-score and for rainfall in years. So we're going to go ahead and let's get the z-scores first with our calculator. Inverse norm. The first one we'll do is the 25th percentile. That has a mean of 0 and a standard deviation of 1. That gives me a z-score of negative 0.674. And let's do the exact same calculation. This time let's change this to 0.75. And surprise, surprise, positive 0.67. That should make sense because the z-curve is symmetric. So of the same area to the left and to the right, same z-score. It's just that one of them will be negative, the other one will be positive. So negative 0.674. Go ahead and write that in place, and let's go to in context. Let's try to remember our mean is 11.7 and our standard deviation was 6.9, I believe. Okay, so let's get to it. Here we go with inverse norm again. We got 0.25, 11.7, and 6.1. That gives us 7.6 inches, or 7.6 inches of rain. Let's do the same thing again for the 75th percentile. That's just gonna, we just need to change one number here and change that to a 0.75 instead. And that gets us 15.8 inches of rain. So let's go ahead and write those numbers into our diagram. Okay, so this has our numbers in the diagram. Remember, we just did the blue numbers, the ones in context. And now we're ready to write out our answer, and it shouldn't be too much of a surprise. So for LAX, Q1 is 7.6 inches, the median is 11.7 inches, and Q3 is 15.8 inches of rain. This brings us to the final part of our problem, and let's take a look at what that is. So whenever there's, well, no, we should read it. In the unusually wet 1982 to 1983 season, downtown Los Angeles received 31.25, LAX received 25.6 inches. Find a percentile rank, and then which location had a more unusual amount of rain. So two things to note here. Percentile rank is just area to the left. And then the other thing is more unusual rainfall. That's the same thing as greater z-score. Both of these things are going to be related. In fact, we could, whichever one has more area to the left, which has a greater percentile rank, should have the greater z-score. Let's go ahead and look at our curves. And actually, both of these amounts of rainfall are so unusual that they probably don't fall on the curve. Let's see, LAX is 25.61. Well, I guess that's on the curve a little bit. And then, okay, so let's go ahead and get those curves. So here's our two z curves. I've only labeled the right side since that's where we're going to be concentrating our attention. And now we've got to find an LAX. We got to find where is 31.25. That should be right about here. 31.25. And then in LAX, we're looking for 25.61. That's right about here. 25.61. We're going to find the z-scores for these. And then we're going to find the area on the left. We'll find this area here, and we'll find this area here. So the very first thing, or the next thing we're going to do is set up our z-score. Probably it would be a good idea to put subscripts here so we know which one's which. So this is the same thing. It's the amount of rainfall minus the mean divided by standard deviation. And that should get us our z-scores. And we'll be able to tell a lot once we compute those z-scores. So let's go ahead and grab our calculator and compute those. Let's see what we get. So we get a z-score for downtown Los Angeles of 7.4 and a z-score for LAX of 2.28. So looking at those rainfalls, even though LAX received less rainfall than downtown Los Angeles, this was a far more unusual amount of rain for LAX. So let's write that summary statement. I know you probably thought I was crazy just now because clearly downtown Los Angeles has a greater z-score than LAX. So yeah, downtown Los Angeles received a more unusual amount of rain because its z-score is greater than LAX's z-score, 2.41 versus 2.28. Next, once we've done that, we're going to answer the second part, which would be find percentile ranks. That's actually the first part. So our percentile rank is just going to be the area to the left. So the percentile for downtown Los Angeles, proportion of rainfall less than 31.25, which is equivalent to the proportion under the z-score that's lesser than 2.413. And in the LAX side of things, we've got the percentile rank is the proportion of rainfall years that's less than 25.61 inches, which is equivalent to the proportion under the z-score that's lower than 2.28. Let's grab our calculator and calculate them both. Starting with downtown Los Angeles, let's see what area is to the left of 2.413, so between negative small number to 2.413, and we get 0.9921. Because I'm extra like that, I'm going to go ahead and compute it in terms of rainfall as well, contextual data, and I'm probably going to run into some issues here because the lowest amount of rainfall is going to be 0 and not those negative numbers that we saw. So let's compute this, and we get 0.9749. Shifting things over to LAX, now we're going to see the percentile rank to the left of a z-score of 2.28, and that gives us 0.9987. 0.9987. And of course, I'm going to calculate this in context as well. Let's see what proportion we get to the left of 25.61. And that's 0.9612. So this one was really off from the z-score calculation, probably because we had to clip more off on the normal curve due to where 0 lies. So 0.9612. Just to keep things a little bit consistent, we're going to say that downtown Los Angeles is at the 97th percentile, while LAX is at the 96th percentile. And that should basically cover it for us. That is the entire thing in a nutshell. So I hope you learned something from that, or maybe in the best case scenario, just reinforced a lot of things that you already knew. So good luck on your test, and I'll see you for Chapter 3.